Hello everyone, welcome to video 1 of chapter 7. So this chapter, the topic is the transportation problem. Let's get started. The transportation problem, as the name suggests, is a type of problem that try to work out a schedule of transporting goods from sources to the locations. These are usually large-scale problems with many sources and locations. For example, we could have 100 warehouses and we need to ship the goods to 300 retail stores. So as you will soon learn, with these numbers, then the total number of variables would be the product of these two. 100 times 300, that's 30,000. And the number of constraints is the sum of these two, so 400 constraints. So it will be a really large problem. So this type of problem is one of the most studied problem in mathematics historically. So let's look into the details. So before we start the transportation problem, we look at another problem called a distribution problem. Later, you will see the connection. So let's say I have some origins and destinations. Let's say m is now the total number of origins, and n is the total number of destinations. And then I have these numbers, ai with index I, that implies the supply available at the ith origin. And we call this OI, origin index I. And I is an index between 1 and m. And at the same time, bj would be the demand at the j's destination, and we call this dj, d for destination. And j is index between 1 and n. So, furthermore, it is also given this number k carries the index ij, a double index. This is capacity. That means the maximum amount that you can distribute from OI to DJ. Okay, therefore it carries the double index ij. Okay, for the problem, we will now define the variable. This is x, carries index ij. That will be the amount that will be shipped from OI to DJ. Okay, so with all these being set up, then I have a bunch of constraints. So first, if I add up xij for a fixed I, and then I run j from 1 to n, this becomes the total amount being shipped from the origin I. And that has to be less than the supply, which is AI. And then this inequality holds for all the i's going from 1 to m. Okay, so this is a constraint coming from the limited supply. And the second line here, the constraints will come from the demand at the j's destination. So if I summing up I from 1 to m for a fixed j, this becomes the total amount being shipped to dj. And that shall be bigger than equal to bj because this is the minimum demand. And this should hold for all j index from 1 to n. And lastly, we also have the capacity. So to ship from OI to DJ, this amount you ship, this is a restricted variable, and then it cannot exceed the capacity, how much you can do. Okay, so this is m constraint, n constraint, m plus n, and then here is m times n. So total m times m plus n, a lot of constraints. So we want to put two remarks. The first one is that we must have this inequality being satisfied. That is, summing over all the AIs, this gives us the total supply in all the warehouses. And summing over all the BJs, this becomes the total demand. And then the total supply must be bigger than or equal to the total demand to even have possible feasible solutions. Okay. Otherwise, if you have strictly less than sign here, then the problem is automatically not feasible. There are no feasible solutions. And the second remark is the problem, this distribution problem, is not an optimization problem. We are not trying to minimize or maximize any quantity. The goal here is just to find a feasible solution that satisfies all the constraints and through some algorithm which we design. Okay? Okay, so the main idea is to go through iterations. So you would start with the first origin, I equals 1, and then we will assign the shipping flow within the constraint. And then you move on to the next, I equal 2, and 3, and so on. And then in the end, you have to adjust and rearrange as needed. And there are many, many details to come here. Okay, so we will take an example and see how this can be worked out. Okay, so this is our first example for distribution problem. So following our notation, OI is the origin, DJ is the destination, and here it's given the table for capacity, the K. So these are the destinations, and here the origin, so 3 origin and 4 destinations. And what's in here is the Kij, say this is K11, shipping from origin 1 to destination 1. And this will be K12, shipping from origin 1 to destination 2, the capacity allowed. And then this will be the capacity for shipping from origin 1 to destination 3, and so on and so forth. So this block here are the capacity. And this constant column here would be the supply at the origin OI. Okay, so this is the AI here. So 5 units at origin 1, 7 and 7 at 2 and 3. Okay, and then the last row here is the destination demand. So for destination 1, it must have at least 3 units, and for destination 2, also 3 units, and 3, 9 units, and 4 units. Okay, so that's data being presented in this tabular form. Okay, so if the data, we make it a convention to always represent it in this tabular form, then we have a more compact way of recording the data, namely just this tabular form. We can drop the D here, the O here, because it's understood the meaning of this tabular. Okay, so we will be using this from now on. Okay, now let's try to see if we can find a flow chart that satisfies all the constraints. So step 1, I will start from the first row and move from left to right and fill in and satisfies also all the constraints. So let's go through it. So row 1, I'm going through. The first one here is from warehouse number 1 to destination 1. And then I see that the capacity is 4. But destination 1 only needs 3 units. So I will ship 3. Okay, then let's look at the second one. Capacity is 1. And the destination needs 3, but I cannot be more than 1. And the warehouse 1 has 5 units. I have taken 3, so I still have 2 units. So I could ship 1 unit here. So we put 1 here. Okay, hope that's clear. Now look at the third column. Now how much can we ship from origin 1 to destination 3? So capacity is 5, sorry. And D3 needs 9 units to be shipped there. But then from origin 1, we already shipped 3 and 4 units out. So there's only 1 unit remaining. So that's all you can take. So you take 1. So after putting this 1, this 5 unit is all being shipped. So there's nothing here. So we leave it empty. That means it's 0. Okay, so that's how you go through the first row, by simply checking how much is needed and the capacity, and then how much is still there in the warehouse. So it could often happen that the first few can be either equal to this number or this number. So you see here it equal to this number, and here this equal to that number, and here it gets smaller, and then for later ones there's nothing left, and then this is no shipping is done. Okay, so once you have done the first row, then we can continue with the second and the third row. Basically follow the same principle. So let's look at the second row, some details. So second row, let's go to the first one. Can I ship anything to warehouse 1? No, because I already have 3 units, so it's done, so nothing here. Okay, and then, okay, so from origin 2, can I ship to warehouse 2? Well, okay, here the capacity says is 2, and the warehouse 2 already received 1 unit, so it still needs 2 units. And then I still have 7 units in the warehouse, so I can put 2 units here. This satisfies all the constraints. Okay, that's 2. Now move to destination 3. Destination 3 says that it needs 9 units, and 1 unit is already there, so it still needs 8 units, and the capacity is 6. So at most I can ship 6. But then from the warehouse 2, I already shipped 2 units out of 7, so only 5 units is remaining. So therefore, you would put 5 here. Okay, and now the warehouse 2 is empty. There's nothing here for this, so it's 0. So that's how you do row 2. So you know this warehouse is empty and this warehouse is empty. Okay, now let's look at warehouse number 3, origin 3. So here the demand is already met. I do nothing. And here destination 2 needs 3 units. And I'm already shipping 3 units, so nothing. Now for destination 3, I have 1 plus 9, which is 6 units, is already being shipped, but it needs 9 units. So I still need to ship 3 units. So, and then the capacity here is 4, so I could ship 3 units. And let's check if I have the amount in the warehouse. Oh yes, there are still 7 there. So I could ship 3 units here, which means I still have 4 units left. Okay, and then let's look at the last one. Well, it's 0. This means you can't ship from O3 to D4 because no capacity, so nothing. Okay, and then you stop. Okay, so this will be the initial attempt, which doesn't mean it's a feasible solution, but it's the first iteration that we put in whatever is possibly feasible. Okay, so now let's look at further. So first, let's look at the 3 warehouses, O1, O2, O3. Are there any surpluses? So we know this is all shipped out and this is all shipped out, but for the 3 here, 7 units, only 3 units is shipped, so there is surplus. And then we mark it with a S. Okay, so this is marked in blue. And now let's look at the destination and to see if the demands are all met. So for destination 1, it needs 3, it's met. And destination 2, it's 3, it's 1 plus 2 is also met. Destination 3, I need 9 units, 1 plus 5 plus 3 is 9. And then destination 4 here needs 4 units, but nothing is being shipped. So it still needs 4 units. This demand is not met. So I'm marking this here 4 in red to see that, hey, pay attention, I am still not happy. Okay, step 3. So here is the tricky step. It can take several rounds of iteration. So here we will try to readjust this flow chart to the goal is try to move some surplus value eventually into destination 4, which still has a demand not met. Okay, and how do you do this? Well, you just have to look at it and see if there are any adjustments you can make. And usually there are many possibilities. So let me explain what I mean by that. So let's see, for example, this flow adjustment that's being recommended here. So what does it do? So I know that row 3 has surplus. I would like to ship some of this out. Then let me look at row 3 and check which column I could increase the shipment amount, and that is those that has not met the capacity. Okay, so I could actually do either here or here, and even here and here. All of them are possible. Let's say we pick this one. So the column 2, C2 here, I increase this on the initial one, say this is 0. Let's change this into 1. So if I make this 1, then for destination 2, between these two, I need to reduce them by one of them by 1 unit because I need only 3 unit total, because now 1 plus 2 plus 1 is 4. Okay, and then you could either reduce this one or reduce this one. So let's say I picked this one. Let's just see. And so I replace it by 1. Okay, and then that means the warehouse 1 now has 1 unit surplus. I would like to increase it, hopefully to column 4, D4, that's where I want. And then I see that, in fact, I could do, because here originally it's 0 and capacity is 1, I could increase this to 1. Okay, so if I do that, make this change, then all the constraints here are still satisfied, and then I would have 1 unit being shipped to D4, and then I would reduce the demand that's still not met from 4 unit to now 3 unit. Okay, so as you can see during the way I discuss about it, I was just picking one of them. You could easily see that I could pick others and get a different flow. Okay, so in fact, we'll look at several other ones now. So let's say I now make this adjustment. I changed these into the green color, and then I still have a surplus here, and I still have a demand not met. Okay, so let's see if we could adjust further. Second round of adjustment. Okay, so again, I have here is a flow being suggested here. So from row 3, where I have the surplus, where could I send out things? Well, let's see. Here, let's say if instead of 3 unit, I send out 4 unit. I can do it because I still have 4 units, 3 units surplus here. So I change this into 4. Then among these, I should reduce one of them. So let's say I picked this one. I reduce this 5 to 4. Then that means I need to add 1 unit somewhere in this row. Okay, could I add it here? That's where I wish to increase. Oh, yes. You see, it's 0 and the capacity is 5, so I could increase this by 1 unit. Okay? Then I shipped another unit in destination 4. And 2 plus 4 plus 1 is still 7. And it's in warehouse number 2 is still all shipped out, no surplus. So all those constraints are met. Okay? And then I managed to reduce the unmet demand still further. Now I have 2 units to be shipped to D4. Okay, and I still have surplus, so I still mark it here. Okay, so we're not done. Let's try to see if we could find another round. Okay, so here is round 3 in this purple color. So let's see. So warehouse number 3 still in surplus. And let's look at the columns. And then we see here it's 0 and the capacity is 5. And let's try to ship 2 units from this. Okay, so I increased this shipment by 2. That means among these, I need to decrease by 2. So let's say now I decrease 3 by 2, so it becomes 1. Then I need to increase 2 units somewhere here. And then we see that I can try here because it's only 1 unit and the capacity is 5. So I increase this by 2 units, I get 3. So now if this is increased by 2, then somewhere down here, I should decrease by 2. So let's see, this is 4. I can decrease it by 2 units and I get a 2. And then I should increase, hopefully column 4, that's my target. I want to increase the shipment here. And I see it's only 1 unit and the capacity is 5. I can increase this by 2 units and make it 3. Okay, so this is a rather long chain of adjustment, but we see now we managed to ship 2 more units to destination 4, and then the total demand that's still unmet now is being reduced to 0, which means the demand is now met, and then I do not have any surpluses in O3, so everything is resolved. Okay, so this means I have found a feasible schedule. Okay, let's summarize. So I just took the final numbers here and listed in this chart. So this is the capacity, Kij, and then right next to it is the schedule, Xij. Okay, so X11, X12, X13, X14, and so on and so forth. And then you can verify that 1 plus 0 plus 2 is 3, 0 plus 2 plus 1 is 3, 3 plus 2 plus 4 is 9, 1 plus 3 is 4. So all the destinations have their demand met, and let's check the warehouses, the origins. 1 plus 0 plus 3 plus 1 is 5. 0 plus 2 plus 2 plus 3 is 7. 2 plus 1 plus 4 plus 0 is 7. So everything is shipped out from the warehouse. And then you see this number is always less than the capacity in all of these pairs that's being shown here. Okay, so that is a feasible schedule. Okay, so so one feasible solution is found, and it might not be the unique one because we made many decisions along the way. Okay, so one comment before I move on. If you read the textbook, it uses a slightly different notation when they were adjusting the flow. So For example, if I replace 3 by 1, well, this is my notation, then the textbook would be just put a cross on the 3 and put the 1 next to it to indicate, and now I remove 3 and I put a new value. Okay, so it's just a notation and both would work. So next time we might use this notation so it's consistent with the textbook. Okay, so that's all for this video. I hope you enjoyed it, and next time we will discuss in particular a strategy for us to find a flow for the adjustment. Okay, so hope you enjoyed it. See you next time.